Our topic for today is the section 1.2, which is implication equivalence. When we discuss implication, we are concerned about the statement that we usually describe more precisely in the form if, then. So basically, if P, then Q. That's how I just label whatever simple statements are there. And generally, this is probably the interpretation that we have to justify the most, because you might be surprised with the way the table of the appropriate operation coding this will come out. So generally, this statement, if P then Q, is coded by the propositional formula P implies Q. And the same way as last time, we'll have the table true, false, and then I need somehow to convince you that actually the way we will fill in the table is actually correct interpretation of everyday language. So here's one example to justify that. Example, if you earn 80% average, then you will get a B, a grade of B. So for example, that's what's really stated in the syllabus. So generally, if you think of this as a P statement, and this as a Q statement, you really have this if-then structure. So then what? So we have, so case when they are both true, no one has any dilemma that this should be true. So basically what? You earn 80% average, I'll give you a B, everybody's happy. Now what? What if you earn, what if you earn 80% average and you don't get a B? Then basically you can immediately complain that I didn't keep the promise I made in my syllabus, so that basically, so that's false, no dilemmas about that. So if that happens, I'll probably need to talk to my dean what happened with my promise in the syllabus. So there's no dilemma, I would say, that this is the way to interpret these situations. But basically, here is where things might look a little tricky. What if you don't get 80% average? So what if you earn 78%? So what then? Do I have a right to give you a B? Probably yes. So if I give you a B, I didn't break my promise, I kept my promise. So this might surprise you. I put true here as well. So false implies true is considered to be true. Why? Because basically my syllabus doesn't oblige me. So either I give you a B or I give you a C. We cannot say that I broke the promise I made in my syllabus, and the same thing here. So basically, we'll make this operation in such a way that the only case when it's false is this one, when true implies false. That's the only situation where we break the promise, or the only situation where implication is not true. Something closer to mathematical examples, let's say the following, example 2. So still I'm trying to sell this decision as being correct. You know, so I cannot prove this, but just I want you to develop an intuition where you really trust this. I hope that you agreed the following. If A is greater than 3, then A squared is greater than 1. So I would say that most of you will say, yes, I know that that's true. If number is greater than 3, then square of that number is greater than 1, and that must be true, because number bigger than 3 times number bigger than 3, that's bigger than 1 for sure. So I say this is always true. Alright, so the other two, okay, let A be 4. And then what will happen? Then this is true, this is true, so you have true implies true is true, we all are happy. But what if I put A to be 2? Then A greater than 3 is false, A squared is greater than or equal to true, so false implies true should be true. I should always get true because that's what we agreed. What if I put A to be 0? Then you'll get what? False implies false should be true, as we said. Why I cannot build the fourth case and give you example? Because that would make this statement false, but we said it's always true. So you commit it in the beginning, always true. So for my different choices of A, it obliges you for this interpretation. So one way or the other, in this course, we will always have that this is how we will calculate the value of the formulas involving implication. Okay. So here are two formulas involving implication that we'll use quite often. So I formulate that in a theorem. 1, 2, 1. The following equivalences are always true. P implies Q is equivalent to not P or Q. Please not only recognize that this is true, but also memorize it for a future. Why is that important? For example, if you want to build a logic circuit, then there's no symbol for implies, then you need to actually interpret implies in terms of things that do appear in the circuit. So that's why this is really a way to trade implication. And also, negation of P implies Q is equivalent to P and not Q. Well, these are so it says if you have negation of P implies Q, that's equivalent to P and not Q. How do you prove that? So prove, just make a table. I'm not going to repeat that on the board, so make a table. Like we did in section 1, or let me do the second one actually. It doesn't hurt to kind of practice this more often. True, false, false, true, false, false. So P implies Q is here only false here, true everywhere else. Negation goes the other way around. Will be false, true, false, false. I need not Q here. I reverse Q. False, true, false, true. And then P and the not Q, it's this line and this line. P and not Q is false, true, false, false. P and the not Q. Oh yeah. Sorry, not P implies Q is false. So when you compare these two lines, because what we did here, negation of that true is false. So when you compare this line, this is our left side, our right side, we got the same values, so they are really equivalent. And by the way, I forgot to mention something, and that is, this line is very often interpreted that says the following: if P is false, then implication is always true. So everything follows from false, or anything follows from false. And then, and this here, It says truth follows from everything. Truth follows from everything. So those two lines are often used in some kind of calculations. All right, what else do we want to discuss here? One more very important theorem about the implication. Let me erase this so that we have a place to write it. And that one we'll call very often. It's called contraposition. So contraposition. And you'll see later on in the lecture, in the chapter, we'll use this as a method of proving. It says the following: P implies Q is equivalent to not Q implies not P. So generally, it's very easy to see that P implies Q and Q implies P in general are not equivalent. So that's called converse. So this is called converse. So statement and the converse are in general not equivalent. The only way you can switch two statements is, so I have P implies Q. If you want to switch them, then each of them gets negation. Again, proof, use table, proof. Table. It's very easy to justify it, but it's very important that we are aware of this equivalence, because it's very often gives us a chance to kind of provide a correct argument that's more convenient for us if we flip the statement but using the negation. And if you open the old exams, you can see that very often I ask you to construct a contraposition of a given statement. Actually, there are different ways to express implication if-then statements, and this is also very, very important, very often used in everyday life and in mathematics. So this example 3 illustrates that. Please pay attention. This is one of the most important details in this chapter. So example 1, 2, 3. Let's say the following. Let P present the following. A number is divisible by 6. Q is a number is divisible by 3. Maybe it would be better if I give that number a name, because if you read it in terms of chapter 2, but I don't think it will hurt. Let's focus more on what we want to say here. So, how would you read the statement that P implies Q? So that says, if a number is divisible by 6, then it is the same number is divisible by 3. So this is correct statement, and we'll talk about divisibility more in a few sections, but right now I assume everybody understands this. So what? The same statement, so you see, here's the construction, and this first statement is, by the way, called antecedents, and this one is called consequent. And then what? The same statement could be expressed in many, using different language. So what is it? If we want, so if we want to reorder this, then we can say the following. A number is divisible by 6 only if it is divisible by 3. So generally, you see, if is always attached to antecedents, and only if is attached to the consequent. And you know, sometimes in the language we sometimes permute parts of a sentence, but this is the best indicator. So only if is connected with a consequent, and if is connected with the antecedent. Someone would even read this first. He would say, only if a number is divisible by 3, we can expect it to be divisible by 6. So a language has many variations of this, but I want you just to pay attention to if and only if. Another way to read this is necessary and sufficient condition. So we'll say the following, that P is sufficient for Q. So that means being divisible by 6 is sufficient for a number to be divisible. It's sufficient for, in order for a number, in order for a number to be divisible by 3. So generally, very often, antecedents is called sufficient condition. And the other way around, Q is necessary for P. So we would say, and common sense confirms that being divisible by 3 is necessary, not enough, but necessary for a number to consider it being divisible by 6. Sometimes, we'll talk about it more when we talk about sets, but it's never too early. So generally, antecedents, sufficient condition is a stronger one, more elite, more narrow, and the Q is kind of more general or looser condition, weaker. So generally we can think of this the following way. So here is USA, and here is California. So when you say that someone is California, then it's more precise information than if you say just person is in the USA, because then person could be in any other state or DC. But so generally what? Being in United States is a necessary condition. If you want to be in California, you first need to be in the United States, and then we see where you land altogether. The other way around, if you are in California, then that automatically gives you that weaker assumption that your object is in the USA. So this is more precise information, and this is more vague. So precise kind of implies vague, and you need to satisfy the vague condition before you satisfy more narrow or more precise condition. And then what? Let me here also illustrate how contraposition works. So in that case, in this case, we will flip them and do negation. So if a number is not divisible by 3, then it is not divisible by 6. And this geographic description, if not in the US, then not in California. I'm making it along with California because so it's not Canada or something like that, then statement gets completely different meaning. All right. One more thing, and that is the other half of this title. It's about equivalence. Generally, that's another operation. That's very simple. What would that be? It's equivalent. So no, I better erase it. Equivalence. So this is the statement P equivalent to Q. So that means this is true if and only if they have the same equivalence value. So true, false, true, false. So it's true if they are both true, so they are equally valid, or both false, and then if they have the opposite value, it's false. This is what equivalence does. By the way, there is a little similarity between this equivalence and then the equivalence between the formulas. This is the symbol that you can use within a formula, because this is the formula, and this is what we call a meta symbol, because it just, in meta theory we talk about two different formulas. So here you see P and Q is equivalent to what Q and P. This is not a formula. This is the formula, this is the formula, this is our comment about the formula. Here equivalence is just part of the formula. It needs special symbol when we write formulas. So here is how equivalent looks like. By the way, it's very easy to prove the following, that P equivalent Q is basically equivalent with P implies Q and Q implies P. That's easy to justify if you make a table, and that's why when we have that P is equivalent to Q, we read it like this. So we say what? P is sufficient for Q, and Q is sufficient, or P is necessary for Q. So then we say in mathematics very often, P is necessary and sufficient condition. For Q. We also say P if and only if Q, because it's necessary and sufficient. And then to make it simpler, because we use that very often in mathematics, you erase all this. And that's official, it's not like slang. This is official in mathematics. We very often write P if IFF Q. So when we say IFF Q, that means that they are equivalent, that they are a necessary and sufficient condition for each other. And generally at the end of the section, you have again a list of some equivalencies that are useful. Some of them we already established during the section, and some of them are just sometimes useful. And then last example in the section, I ask you the following. So this is example 1, 2, 4. Is it true that P implies Q implies R is equivalent that P implies Q implies R? So that's a question. So is it true that basically what we did here, we just rearranged parentheses? So what happens here? Generally, if you write the whole table, you can see that they are not equivalent. So how do we establish that? In my notes, I just gave that one line showing the valuation where they are different. But so Just so one option is do the table, and I better do it because it's the first time I think I'm showing you three letters: P, Q, R. True, 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 true. False, 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 false. Then true, true. False, false. True, true. False, false. True, false, true, false, true, false, true, false. Here are 8 options. So P implies Q. And then here's Q implies R. So P implies Q is true, true, false, false. From false everything is true, so here are 4 truths. Q implies R, true, false, true, 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 false, true, true. Alright, I hope I did it correctly. If not, we'll go back to check it. P implies Q implies R, so from right to left. Q implies R, give me true implies true is true, false, true, true, from right to left, true, true implies false is false, true implies true is true, true implies false is false. That's left side. What about right side? P implies Q implies R. P implies Q implies R. So this one, first or right, it would be true. True implies false is false. So far is good. P implies Q implies R is true. True. So far it's good. False implies Q is true. False implies false is true. Stop. I don't need to finish it. Here it is. This one has false. This one has true on the same valuation line. So not equivalent. There is a shorter way to do it. You don't have to learn all these methods. Table is the safest way, but sometimes we just kind of hesitate to write so much, and maybe we can make calculation errors and so on and so on. Sometimes doing it conceptually might help. And one of the methods is discussion on the letter. So what? Two cases. Case 1. P gets the value 2. Case 2. No. You know what? Why don't I discuss it on R? Sorry. You see, it changes R false. Why did I decide to do it? If R is true, then the top is true. Why? Because true follows from everything. So left side is true, and right side, Q implies true is true, P implies true, so they are both okay. So if R is true, I'm done. So generally with this little thinking, I did all 4 lines that have R true. Look how simpler is this than writing all these lines. So what if R is false? Then generally what? If R is false, then I can do the cases. So what do we do here? Then probably I will do or let me use these equivalencies. I don't know how familiar. No, it's too complicated. No, let's do the subcases. So let P be true, and let here P be false. So if P is true, then what will happen? True implies Q. If Q is true, it will be true. If Q is false, it will be false. So that's the same as Q. So this says Q implies R was false, false. That's what the left side is. right side has T, this is true. So true implies something is the same as that something is. So this is Q implies false. So if P is false, no, I calculated it wrong, sorry. So left side is Q implies false, right side is what? If P is false, false implies everything, so this one is always true. So here it is, right side is always true, and left side says Q implies F, so it depends on Q. So what if I choose Q to be true? Then this becomes false, this one's true, done. And that's exactly how we recovered the line where what? R was false, Q was true, P was false. So here it is. So so that's how all of that should be written here. So Q is true. So you get true implies false, which is false here. That case, not that one. So one way or the other, this is the way how you sometimes. So previously we showed how to show that formulas are equivalent. Here we showed in two different ways how to show that formulas are not equivalent. So let's summarize. So in these two sections we kind of introduced our four operations that we use to build propositional formulas. Five actually, sorry. Negation is a unary symbol, then and, or, implies, equivalent. So we have these five operations, and now we can legally use them to build formulas. And we are interested in the following question: when are these formulas true? For which valuations they are true? For which ones they are not? If they are true for all valuations, it's called tautology. True for all valuations. Opposite of it is contradiction. Always false. So this kind of introduces all the formal machinery, and then in the second half of the chapter we'll try to see how can we use that to analyze valid reasoning or correct reasoning, and also how is that used to build logical circuits and to add up numbers using machines.